Hey everyone, how's it going? How's everyone's reInvent going so far? Pretty good? All right, nice. Well, I want to talk to you today about my company Braze, and in particular about auto scaling, and essentially how we use AWS Auto Scaling to help us send a lot of messages to end consumers in the cloud. I actually updated the slide to over 2 billion messages because now we're sending over 2 billion messages a day to folks. So to let you understand what I mean when I talk about messages, I want to take a minute and just talk to you about Braze so you can understand the scope of our business, the scale at which we operate, and the types of problems that we solve. So Braze is a modern, comprehensive customer lifecycle engagement platform. We help consumer brands use data to personalize and deliver great customer experiences through messaging. And when I talk about messaging, I mean things like sending personalized emails, push notifications, in-app messages, SMS messages, really any communication that a brand has between themselves and their end consumer. We want to help make that relevant and timely and personal, add value, and ultimately build a strong relationship between the brand and the consumer. So chances are probably already in your pocket. If you ever gotten a push notification from Postmates letting you know that there's a 10% off sale on delivery tonight, that is orchestrated and sent to you through Braze. Or if you ever get money from a friend on Venmo, you withdraw it and then see an in-app message to put that money on a Venmo debit card. That in-app message is served to you through Braze. We're very plugged into the digital world. Across our customers, we cumulatively engage over 2.1 billion monthly active users, and we're now sending over 2 billion messages a day. In fact, on Black Friday, we sent 3 billion messages, which was a huge milestone for us. We're really excited about that scale that I'll talk about today. So just to kind of give you the background about why this is also important is if you think about how the digital economy has kind of formed, we all know that computing really changed when it started getting into the enterprises. But for me, the story starts when mobile kind of came out about 10 years ago. Because all of a sudden now you have a lot of consumers having a mobile device and they're interacting with brands through different platforms and channels, operating online and offline, and now they're generating a ton of data. And there are some really well-poised brands that were able to take advantage of this. Companies like Google and Facebook, the company that hosts this giant conference. And what they did is they've actually raised the bar in terms of consumer and customer expectations around personalizations. You can actively get upset if you get like a bad ad. Like I watch like Hulu and I get like an ad for arthritis medicine. I'm like, hey, I'm watching Broad City. Like, why would you show me this? Like, it's silly to not target this toward me. Like if I was watching TV, I get it. But when I'm online, when I'm interacting on my phone, I expect the brand to have a really solid understanding of who I am and tailor things toward my preferences. So that's what we help customers do. So today's talk, though, is about scaling, and in particular, scaling on AWS. So I want to first start by breaking down the two main high-level categories of data processing that Braze has that we're going to talk about with the auto scale. So the first is just general data processing, collecting events from mobile apps, websites, inboxes, like if a customer opens up an email, and then taking action on top of that. So essentially, every time someone downloads a mobile app that Braze is in, or they visit a website that our JavaScript SDK is on, we then start creating a user profile on who that consumer is so that we can help the brand deliver great targeted and personalized notifications and messages to that consumer. So essentially, if you say open up the Postmates app or Venmo, or you visit a website that we're on, then that data is going to come into Braze, letting us know that you are now using that product so we can help the brand help engage you. So cumulatively, we're ingesting a ton of data from mobile devices. And then we also have a set of REST APIs that our customers can hit in order to ingest data server to server. So if they want to give us information from their back end or ingest data from the offline world, like give us store purchase information, they can do that. So collectively, this is millions of API calls every single minute. We have some extremely high spikes at Braze. And what is important for us to think about is that every piece of data that we ingest is extremely valuable for us to process immediately. So we're not like an analytics company that's going to just show you some graphs, so it's okay for us to batch. For us, and the whole value proposition is around engaging consumers in the way that they have the expectations around being engaged, which means real time. And when we think about real time, we think about the immediacy of like a conversation. Because every piece of data we get could change the audiences that a consumer is in. Every message that a consumer that we need to send now needs to be accurate to understand that we're targeting a user with the up-to-date information. Like if I wanted to send a push notification to everyone to watch Game of Thrones, and I've already started watching that episode, now that's going to be a bad experience because ultimately I'm in the middle of watching it and now you're interrupting me. So we want to ensure that we have the most recent up-to-date information on what the user is doing. Similarly, any piece of data that comes in could cause a message to be sent. For example, if you're SoundCloud, another one of our customers, and you want to recommend other songs to us based on things I'm listening to right now, we want to make sure we get that in a relevant and timely manner and send you that message. It also could cause messages to be canceled. So take that Game of Thrones example where if I'm already starting to watch something, you don't need to send me a message. So our whole value prop relies on us processing data very, very fast. Besides data processing around events, we also think about message sending, because that's really what a lot of our customers are using Braze for, is to orchestrate their customer lifecycle. And there are a number of different types of message sending that our customers can do with Braze. They can send things immediately, so just essentially logging onto our web dashboard and hitting send right now, and they expect that message to go out instantaneously. They can schedule campaigns to go out, so if they want something to happen Friday at 5 p.m., they can do that. Or they can do more of those real-time triggered-based things. So we have something called action-based campaigns that send when users take action. For example, you can make a purchase and then get a survey or receipt email following from that. We want that to trigger off of an event that comes in. Or it could just be API triggered in general, where our customers tell us when to deliver the message and to whom, and then they want us to deliver it very quickly. But more sophisticated customers are building full life cycles, and I have kind of an example here on the right of a customer journey. These are things that are multi-day, multi-message, and multi-step strategies that contain a lot of business logic around what messages we're sending to users. You can imagine an onboarding campaign that emails you the first day you start using your product, and then the next day uses the actions and behaviors you performed to figure out what message they should send to you next. This is the type of strategy they can use in order to execute that. Now, but ultimately, our customers want us to send their messages really, really fast. And what's important to know and think about in the world, which is just obvious, is that SLAs are never going to go down. Customers are always going to want us to send even faster than we're sending today. And it's a challenge as we get more customers, because we then have more messages in total, cumulatively, for us to send in general. So what we could do is just throw a bunch of money at the problem and typically just try to scale up our servers as much as we can. But a reason that we think about AWS Auto Scaling is that the cost function to us is actually real. We're building a real business. We want to think about our bottom line. There's no infinite resources. So the problem and challenge and question we have to ourselves is, how can we process data as fast as possible? How can we send these messages as fast as possible without it breaking our bank and it being cost efficient for us to run our business in a smart way? So to answer this question, I first want to talk you through our data infrastructure and how we store data and how we process data and isolate our customers together. So I mentioned to you that every time a consumer downloads and opens up a mobile app that we're in or visits a website we're on, we create a user profile on that consumer. It's like a 360-degree view of all of their activity across different platforms and devices and channels. We store this in MongoDB, and we have a database deployment model where we actually store different customers on different tiers of databases. So ultimately at Braze, we have dozens of database clusters. So each database cluster is composed of a number of primary and secondary databases, a number of shards, load balancers, configuration servers, and all of that. But the way that we think about them is we can have a shared database. And the way I like to kind of use this analogy is a bit more like Excel. Like imagine that I've got one giant Excel file, and in that Excel spreadsheet, I've got data for customer A, B, and C, and I have like a foreign key that just says it belongs to company A, company B, or company C. That's how a lot of databases just tend to work. You just put a foreign ID column in there, and you're kind of set. So we do that with small customers. Let's say you only have 100,000, 200,000 users. We can just get a lot of efficiencies by packing a bunch of small customers together on our database. But as you start to get bigger, as you become companies like Lyft or Venmo or Postmates, then we need to start thinking about how we can be more efficient with your database. You might have tens or hundreds of millions of users. You might have a tremendous amount of data that comes into Braze. You might be sending tens to hundreds of millions of messages from Braze. All of those are going to have reads and writes. And we're thinking how we can better isolate it. So in that Excel spreadsheet example, instead of having one spreadsheet of customer data, we now could have a file that has different tabs. And one tab is Lyft, and one tab is Venmo, and one tab is Postmates. In this way, we can have it separately. And an advantage of doing this is that we can scale our hardware out such that we can essentially allow one customer to burst out to the amount of hardware that we're giving it. So let's say that I want to build a database cluster that has 300 gigs of RAM, 20 shards and a bunch of CPUs, well, maybe one of our customers doesn't need all of that all the time, but when they send that Black Friday campaign, we want to make sure that they have a lot of resources available to them. So that's essentially what this middle section is, or our medium kind of clients are. But then we have really big clients like SoundCloud, where they have, again, hundreds of millions of users, an incredible amount of messages. We want to make sure that they have all the RAM, all the CPU, and all the disk they can that's just totally dedicated to them. And this helps us from an isolation standpoint, which I'll get into in a little bit. But it's really important to understand this is the foundation for which we scale all of our thousands of customers at Braze. Now, around these databases, what we do is we then build pools of worker servers. And what I mean by a worker server is simply an EC2 server that processes data or sends messages. And we're going to build different fleets of worker servers around each database cluster that only process data and messages for that cluster alone. So the way in which we actually implement this is that we use the job queuing paradigm. So how many folks here actually use job queues for their own processing at work? Okay, there's a handful of folks. So I'll just kind of describe a bit what job queues are. But it's essentially an architectural pattern to have asynchronous processing. If you want some work done, you could do it right now yourself, but that would be synchronous. Or what you could do is essentially take this piece of job that needs to happen and put it on some queue and let some other process pick it up asynchronously, process it, and then do whatever happens next. Now, essentially, that's what we think about with worker servers. Worker servers are going to be servers that pick up data off the queue. So if I look back in the application flow of how data comes into Braze, you've got a client device, you open up the Lyft application or Postmates. That data is going to come to Braze's API server, which is running on EC2. That server is going to push something into a job queuing database. We use Redis in order to manage our job queues. And then we have an application server that's constantly polling that Redis database to say, hey, do you have any work for me? Do you have any work for me? Do you have any work for me? And if it has work to do, it fetches it off it and then processes it. Now, the job queue paradigm is really nice because it creates a lot of different abstractions. You can create different types of queues. So we have queues for things that are like maintenance that don't need to happen now, so we can just have a few number of servers that handle them. You can have queues for, again, data processing, message sending, data export. You can have a queue for billing. You can really do a lot of different things there, and you can scale that out a bit horizontally and just continue to have a good abstraction. So when we look at our job queues, we process billions of jobs every single day. And we actually do this with dozens of Redis servers. I think all in total, we have something like 40 Redis primaries and 40 Redis secondaries that are handling our job queues. Each job queue is hitting about 200,000 ops per second at peak. So doing millions and millions of job operations a second in terms of Redis. And the way that we did this is we use a third-party library called Sidekick. We're a Ruby-based shop for this processing. But we have done a lot of internal modifications and changes to build application-based sharding for our processing, and also internal tools for us to manage this sharded process and manage all these multiple shards, because, again, we have dozens of them, so we have to be able to solve it through automation. So if we look at a high level how the queues work, you essentially can have different queues that correspond to different databases. And so if event data comes in for a customer on database 1, they're going to go on that queue. If data comes in for a customer that's on database 2, it's going to go on the middle queue and so forth. And then each worker server is going to process a specific set of queues. So this worker only processes Q1, this one only processes Q2, and so forth. And there are some benefits to why we do this. We didn't used to, but one of the first challenges we had was to think about how do we isolate workloads. We want to think about this from a security perspective and from a compliance perspective, which is one part of it, but really we think about performance and quality of service. Databases go down, databases can hang. We have had a tremendous number of issues just kind of keeping up with the amount of scale that we have to kind of put on our databases. And if, let's say we're sending messages for customer A, and then their database has a problem or there's something going on there where it's slowing down, maybe there's a bad index query being used. We don't want it to affect customer B's throughput and quality of service, because that would be bad. We have 1,000 customers. If any one of them could impact our entire infrastructure, that would be pretty challenging for us to manage. So we can think about it from a stability standpoint, but we also can think about it again from scalability. I can now scale this worker fleet separately from this worker fleet based on what I need to do, how much data is coming in, how many messages that I have to send. It also helps us for maintenance. So when we do a database upgrade, we can actually just pause processing. I can just stop consuming from Q1. All of a sudden, I've just killed all the reads and writes to a database. So we can do whatever we need to do in order to upgrade versions, restore, make a backup, scale it out, move customers across, anything else like that. But again, the important part in what this talk's really about is that this allows us to scale very precisely exactly what we need to do in a very targeted manner. So if I think about the Braze message sending pipeline, there's a couple of different steps that go into it for when a message is supposed to be sent until when it actually gets out there. Now, there are a few things here. The first is that we have to go through our audience segmentation step. And this is us just ensuring that we are going to find the right audience to send to. Let's say that it's a Black Friday email, and we want to bifurcate the audience and send to people who've spent more than $50 and people who've spent less than $50. Well, the first thing we have to do is run some database query in order to determine who is in that audience for us to send what message. After we figured out who's in the audience, that's when we start thinking about business logic. So we can understand things like, are they even eligible to receive the message? Maybe it's an email, and I don't have an email address on file. Or maybe I've unsubscribed from email. Maybe you're sending an Android push notification, but I have your iOS app. So we need to think about who is going to get it, what channels are they going to get it on, and when. And then we can think about the frequency capping logic around it. And what frequency capping is our customers can say things like, a consumer shouldn't get more than 3 messages a week, or they shouldn't get more than 1 marketing message a day. And we want to ensure that we are not violating those caps before we send the message. The last couple of steps essentially involve us rendering the payload, so figuring out what is the email to send, or the push notification, or the text message, making these database writes to MongoDB so that we have a record that we are sending this message, and then actually delivering the message to a device, to an inbox, to a phone, to a web page, and whatnot. So there's a number of different parallel processes in terms of getting this done. So when we think about job queues, if I had one job queue for all of these things, these essentially are going to process a little bit serially. Like, a problem with job queues is that you end up with what's called queue starvation. And what it comes from is basically, if you're doing things on a first in, first out basis, then step 2 basically has to wait for step 1 to finish. Like, if I want to send 10 million push notifications and you want to send one of them, well, I got my 10 million jobs on the queue first. So you got to wait for all those to cycle through before yours are going to run it all. So one of the main things that people do to handle queue starvation is they can scale their queues out. I mentioned you can have queues for maintenance and data export and billing and whatnot. But the first thing people tend to do is they use weighting. They think about priorities. I've got like a high priority queue, a medium priority queue, a low priority queue. I can weight them, so maybe I'll check the high priority queue twice as often as the medium priority queue. And this isn't like a bad design. There's lots of literature on blogs that talk about people doing this. It's very effective. I think even Shopify still does something like this for some parts of their infrastructure. It can be very effective. But for low frequency events, it's fine. But we're ingesting a ton of data. I didn't mention it earlier, but we're ingesting over 500 billion pieces of data every single month. And again, sending billions of messages a day. We can't operate like that. So we think about queue weights. We're like, okay, this isn't like a bad idea, but ultimately what makes this challenging for us at Braze is that the concept of just having a static number of queues, a high, medium, low priority, just doesn't work. There's 2 main problems here. One is, well, it's still FIFO. So if I have 1,000 high priority things and then you put a high priority thing on there, I've got to process those other ones first. But also, if there's not a lot of work to be done, I can be inefficient in terms of round trips that I'm taking to the queuing database. And at our scale, we need to consider all possible sources of latency. And let's say that it takes me 1 millisecond round trip to check Redis to see if there's a job. Every queue that I reach out to Redis to say, is there a job here, that I get back saying there's no work there, is like wasted in added latency. So what we really want to do is we want to increase the probability that a worker server reaches out to Redis, asks for a job, and actually gets a piece of data back to it. So we thought about, okay, what if we did like 1 queue per customer? And that seems somewhat reasonable. But again, if you've got customer A sending 10 million messages, just put it on their queue. Customer B sending 1, you can put on theirs. That's fine. But this ultimately doesn't solve the problem. It just increases the span out factor. And it also doesn't solve the problem of the message sending pipeline, that if you had 1 queue per customer, well, all the audience segmentation queries have to finish, then all the business logic has to run, then all the frequency caps have to run, then the rendering, then the sending. it's still not effective. What our customers want is they want to hit go and send a campaign, and they want it to like be on their phone right now. So the way that we did this is we built our own internal dynamic queue system. So what we're going to do is have queues that pop in and out of existence on a per customer and per pipeline basis. So if I'm sending a campaign for campaign A, and that's running an audience segmentation query, that has its own queue. Campaign A also has another queue for the business logic, and another queue for the rendering of the payloads, another queue for the sending, another queue for the database writes. And every campaign and every customer then gets their own amount of queues. So we can actually fan out to thousands of queues at a time. A lot of our customers send scheduled campaigns on the hour. You would think that a marketer would try to make it random, but in fact, like over 90% of all scheduled campaigns are like at 2 p.m. or 3 p.m., not at 3:17 p.m. when it's probably, could be a little more likely to be read because they're not getting bombarded by other deals. But what we need to think about is that we can have thousands of different queues, and this is nice because now we can essentially have more optionality on how we process that data. We can scale up more workers to process different parts of the campaign, to process campaigns for different customers, and we can also then continue to do another weighted selection on queues to ensure that, for example, we're prioritizing getting messages out versus the database queries. So by means of example, let's say I'm going to send to 50 million people. I've already found 10 million of them. We can continue to prioritize that sending ahead of adding more results into the back end so we can get messages out as fast as we can. So that is the queue kind of background that's important to understand how it comes to our use of AWS Auto Scaling, which we're now about to get into. So we think about how we process all of this. I can start with the goals that we have, and I've kind of been stating them over and over again. We ultimately want to process data and want to send messages as fast as we possibly can in the most cost-efficient manner for Braze. And so we want to be able to think about how can we scale up with respect to whatever we need to scale up for, and how can we anticipate that? So that's where AWS Auto Scaling comes into play. How many folks here are familiar with AWS Auto Scaling? How many people are using it in production? All right, so a good number of folks. So some of this will be familiar to you. But basically, at a high level, what we're going to do is, in our system, we want to collect metrics on all of these different job queues. And then we want to have some process that's going to run periodically and is going to look at all these metrics, do a little bit of math, figure out how many servers that we actually need, and then scale the servers up and down automatically. Now, this thing that handles all that is AWS Auto Scaling. So what AWS Auto Scaling is it allows you to create what's called an auto scaling group. And you can define it with a name, you put it in a region, an availability zone, and then there's three kind of components to an auto scaling group. The number of instances that are desired, the minimum and maximum ones. Essentially, the way this works is if you change the desired count, Amazon will automatically scale servers up or down. So if I have 2 servers online and I move desired to 10, AWS will automatically scale up 8. If I then move it down to 5 desired, AWS will scale down 5 servers for us. So this is the technology that underlies all of it. So what we're going to do is we're going to create a couple of different auto scaling groups per database port per AZ. Now, I mentioned database port here because if you kind of remember back to me talking about our database architecture, we have dozens of clusters, and we put our customers on different clusters. So each cluster has a port. So maybe one shared database has port 1111, another one is 1112, 1113, 1114, et cetera. In this example here, I'm looking at 11374. And we're going to create 2 different auto scaling groups, one for data processing, and then one for message sending so that we can split that out. And this is all controlled in Terraform, so even though we ultimately end up with a ton of autoscale groups, it's really easy for us to manage. In fact, we have over 500 autoscale groups to manage all of this infrastructure, and it's very seamlessly done in a .tf file that's easy to read. So what feeds this is essentially a set of metrics around what's going on in our job queue. We can think about, since we're doing this on an availability zone level, like one ASG, auto scale group, per availability zone, we can look at job queue stats per availability zone. We also want to look at job stats per database port per availability zone. I didn't show that graph because it's just insane. Like it is unreadable by a human. We can look at overall queue statistics, how many messages we have or jobs to process on data processing queues, on message sending queues, what's our processing per second rate of data that's going in. And then we can think about what jobs are coming up that we know to be scheduled. If we know that we have a campaign that's going out at 3 o'clock today that's going to send to 50 million people, we can scale up at like 250 just so we make sure that we got enough servers online right before it's going to go out. So these are some of the high-level factors that go into this. And we track all of this in Amazon CloudWatch. So Amazon CloudWatch is a way for you to track application metrics and monitor things going on in your application. You think of it like Stats D. You got counters, you can got kind of gauges and other things like that. Now, a reason that we use CloudWatch is that it actually is the only service we found that has the performance and consistency requirements for us to rely on it in production. What I mean by that is CloudWatch, if we report queue sizes, they're going to then allow us to query for the queue size and have it be accurate and consistent basically immediately. We thought about running our own Stats D server. We thought about using Datadog for this. We thought about using Wavefront, which actually is what these graphs are from. The problem with all those three things is that they're not essentially intended to be guaranteed that they're going to be consistent immediately. So in order to rely on it for production usage, we wanted to make sure that we, at all times, had a completely accurate programmatic view into our job queues and into what's going on by port that we could read from another AWS service, and that was what CloudWatch was the thing for us. So we have a process that runs every minute, and it checks all of our shards. It looks at all the queues there. It publishes information around queue size, queue latency, meaning how old is the oldest thing on that queue. And then it can push it into CloudWatch. So here's an example of one of our metrics. We actually have thousands and thousands of CloudWatch metrics because each queue, each port in each region, in each availability zone, has a number of different metrics on it. So you can see here we can look at how many things are scheduled in the next 60 minutes, how many things are in queued on the specific ports, and then we can kind of graph that effectively in CloudWatch. But what's important here is that this is all accessed programmatically, because the final kind of component in how we actually accomplish this is we use AWS Lambda. So AWS Lambda is a technology been around for a few years, kind of kicked off the serverless kind of trend with Amazon. It allows you to run code in a serverless fashion. You just upload a script, and then you can set it to run whenever you want on a cron, based on an event, whatever. And so we wrote a very simple Python script. And what it does is it first is going to actually read from Fastly. So I didn't even talk about this yet, but we want to think and understand what's the request rate coming into Braze? How many API calls are we getting across our APIs to just make an estimate of how much data do we think is flowing into our system right now? We then also want to read from CloudWatch to look at what are the current queue stats. Again, like, are we backlogged on any queue? Are we backlogged for message sending? Is there a huge amount of messages that we think are going to go out in the next 60 minutes? We keep track of understanding how many messages per second an individual server can do, and then we just do some math. So this is like not like crazy AI, this is not ML, this is like a very kind of simple spreadsheet style formula for how many servers we want to do. And then every 2 minutes, we spin servers up and down. And you can actually see this graph here on the bottom, maybe a bit hard to see in the back. This is the number of processes that we have running. I think I did this over a 24-hour period. And each line represents the number of online processes that are running. You can see here that we scale up really large, it stays there for a while, scales down. But importantly, and interestingly enough, the graph is in constant motion, because we actually cycle through over 10,000 EC2 servers every single week, because we're just constantly spinning things up and down. But this is good for us, because it leads to positive outcomes. If we look at the average latency from our REST API processing, we actually have it at less than a second from data being ingested until it's fully processed. And being fully processed means we've updated all of our analytics, we've updated any audiences, we've sent messages, we've canceled messages that needed to be canceled. And if you look at the bottom here, it's just kind of another view of that graph I just showed you. Our number of in-service EC2 instances is, again, in constant motion, but is fairly sinusoidal as it goes with just traffic that we have. So there's a couple of different outcomes and improvements that we can make to this. we've started doing things like creating different auto scaling groups by function. So for example, I didn't even break down different types of message sending in our groups, but customers think about things in terms of marketing or transactional. If I've got a reset password email, that's just got to get out, again, as fast as possible, and it should take priority over things like my newsletter that I'm also sending to millions of people. So we can create auto-scaling groups that only process transactional messages, and we can also do that on a per-customer basis. So we can give customers a quality of service guarantee of that we're going to deliver their messages in a certain amount of time, which is really important for us at enterprise scale. But we can break this up into other functions. So we are now creating auto-scale groups for message types. So we can have an auto-scale group for emails that just render emails. So when we handle big bursts like we got on Black Friday or Cyber Monday, we can have an auto-scale group that just processes a specific type of data that comes in from us. It allows us to have a lot of flexibility in terms of what we built. But there's other metrics that we can continue to add in to auto-scaling. And so we want to figure out how we can be more predictive of what's going to happen, what messages are going to come, look at historical behaviors, and we want to make it smarter than like a very simple kind of spreadsheet-like formula there. And that's where actually EC2 can help us with that. We haven't started with this yet, but they introduced something a couple months ago called predictable scaling. And what this is it allows you to scale your servers and your auto-scale group essentially in their hands. They will look at historical patterns, and then they will like fit them to some own model that they have here. So I have a screenshot. You can see kind of there's a number of different knobs you can twiddle and mess with. And on the right is another screenshot, again, from Amazon over what is like predicted versus actual. And it's possible this makes us more efficient and saves us money with a better quality of service, but it's something that we need to look into and consider. So with that, I am kind of at the end of the talk. We do have about 10 minutes left for questions. So if folks have some questions, I'd be happy to talk through that. Otherwise, I appreciate you coming out tonight. Any questions? Yeah. So the question was, how do we keep CloudWatch costs in check? That is a great question. CloudWatch, I didn't want to say it, is incredibly expensive. And we actually have to kind of spend a lot of focus to ensure that we're using all the metrics that we're reporting into it. And CloudWatch bills on a per API basis, so making sure that we're batching as much as we can. But it's kind of an area for optimization for us because it can be really expensive for us to add metrics to it. And we're just essentially bundling it in, including it as our cost function of it's just necessary to save us a bunch of money on the back end. So the question is, have we thought about EC2 to container type cost savings? And the answer is yes. In fact, there's some of my coworkers here on our DevOps team who have been spearheading our entire move of all of our platform to Kubernetes and full containerization of our product. So we started the company in 2011, and in 2011, there wasn't really a container ecosystem. We built things kind of what is now, I'd say, the older way. But we want to move everything to containers, and we're actually starting doing that now. We just launched the fully containerized staging environment about 2 weeks ago, and we're going to slowly start to migrate other parts of our infrastructure over to it, because yeah, it's going to see a lot of savings, and we see it in other parts of our infrastructure too. Like this just covered processing, but for example, we have our message sending actual microservices that talk to Amazon, talk to Google, talk to Apple, talk to ESPs and whatnot. Those are all in Golang, and then we containerize those. And so we've seen a good amount of improvements on moving that over. So the question was, what's our data structure like? So there's a couple different things that we just generally I would kind of talk about in terms of the data structure. We use MongoDB as our primary database store. But we use a lot of databases. We use Mongo, we use Postgres, we use Redis. We're using Snowflake for our cloud data warehouse. We have a bunch of caching layers, things like that. But essentially what we think about is our customers are creating a campaign, which is going to be like a MongoDB document, that defines an audience, which translates into a query across other databases. And so when we think about having a user, so again, you download and open one of our customers' mobile apps, we have a MongoDB document that has information around your user profile, so we can help provide a great customer experience to you. And so that's just all, again, going to be stored in MongoDB. And we kind of denormalize a lot of information to be as fast as possible, because what we care about, again, is rapid time to identifying what audience you're in. We don't want things to be stale at all, so we actually have the same piece of information duplicated in a number of different schemas. So we have a number of different views of you, at like a 50,000 foot view, a 10,000 foot view, a very granular view that we can query in order to, based on what we need to do to make a determination of what audiences you're in. Cool. What else can I help answer? All right. Other than that, thank you all so much for attending the talk.